Question.
For the normal force, sorry, I'm so.
You're fine.
But for the normal force, since it's curving downward, wouldn't the normal force be pushing it downward still? For like this specific scenario? Because if it's holding it, like this is on a horizontal plane, and it's curving this way, wouldn't the force turning it left be the normal force?
We can guess either direction, and we will get the correct answer. So, either this thing is moving, and it is in contact with this bottom surface of the rod. So I don't know exactly how it's moving, right? And I haven't solved the problem. I don't know the velocity, acceleration, nothing. If it's moving fast enough, you can imagine that it's maybe slinging out towards the edge of the curve, in which case the collar is in contact with the bottom surface of the rod. Yeah. In which case, maybe the normal force, it still depends on the acceleration, whether that's a positive force or a negative force. Or it could be moving very, very slowly, or I don't know. It could be in contact with the other side of this rod, so that it could be sinking down like this. We only consider one contact point, right? It's either on one side or the other. We're not assuming, we always do point contacts in this class. We're not going to cover a distributed load. That's a different course. Okay, so for this class, when you have a collar on a rod, you either assume the force is on one direction or the other, but it turns out it doesn't matter which you choose. If I guess wrong, if I guess that normal force is up and I solve it and it was really down, I will get a negative number. Okay? Okay, very good. Why am I covering free body diagrams again? Because we're going to start using them. So far in this class, we've covered kinematics. That was what we covered in exam 1. We talked about positions, velocities, and accelerations, and we talked about those things for both particles and for rigid bodies. And we talked about 3 different coordinate systems, and we did it all again for particles and rigid bodies, right? We talked about the Cartesian coordinate system, the radial and transverse, and the normal tangential. Now we're going to move on to talking about forces, but we don't get to leave behind any of our kinematics. Remember at the start of class where I said the big equation that we always need to use in this class is that the sum of the forces equals mass times acceleration? We've learned about the right-hand side of that equation, the acceleration part of that equation. Now we're going to add in the forces, but the accelerations don't go away. We're putting together the pieces to write this whole equation. Forces on the left, accelerations on the right. Okay, so now we're starting what we call kinetics. And specifically, just like we did for kinematics, we're going to start with particles, and we will build up to rigid bodies. Okay. However, before we move on to that, let's talk about exam 1. Okay. I'm not pleased with the average. This is not entirely abnormal for this class. I've tried lots and lots of different ways to try to make it clear that this class is hard and that you will need to adopt new study methods that you might not ever have had to use before. So that might be that you have never needed to go to office hours before, and now you need to start going to office hours every week. Okay? It might be that you were the A student in high school and you never had to go to recitation, or you never had to find extra example problems beyond the homework problem set, and now you do. That's what this class is. This is where you find out where the rubber meets the road. And for whatever reason, it takes not so great first exam grades for a lot of students to realize that the study methods have to change. Okay? So, I am not curving this exam. One of the reasons I'm not curving this exam is that max score. Several people got 100% on this exam. I can't curve that. That tells me that the exam that I gave you was reasonable, it was solvable, it was doable. However, I'm not pleased with the average, and what I don't want is for one single exam to make you feel like you can't do this, or that it's impossible to come back from a bad exam score, because it is possible. So, I'm going to adopt a new policy that I've never done before, but some of my other colleagues have done. What I'm going to say is the final exam in this course is cumulative, and so you have a comeback chance. I will not allow your final grade in this course to be any less than your final exam score. So if you grind your gears from now until the final exam, you learn this material that didn't click for this exam, you get it all right on the final, and your final grade is higher than your course average, I'll give your final grade as your course average. Okay? This is your chance to learn it and show me that you've learned it. All right? Other than that, I'm not curving this. This is as it stands. Okay? Yep, question?
So, hypothetically, if I had a 0 in the class and I got 100 on the final, that would be it?
Yep. Yeah. What is the final exam supposed to show? What is the point of a final exam? Tell me. If you've mastered the material, show me you mastered the material. Okay? Now, that puts a lot of pressure on the final exam if you're making a 0 in this class. I don't want to be calling the ER because you fell out of your chair and panicking, okay? So let's not wait until the final exam to change our study skills. All right? Any other questions? Yes?
So there's besides the final, there's exam 2.
Yep.
So will the final exam like be focused on those last chapters, or I know it's cumulative, but is it going to be more biased towards those last chapters?
I haven't written it yet, so I haven't quite decided. Because I'm doing this new, like, show me that you mastered it, I'm probably going to try to spread the material a little more evenly than I've done in the past. So not weight it more heavily on the most recent material, but actually try to spread it across, like, the 3 chunks. But I haven't written it yet, so that's my plan, to be more in accordance with the reason why I'm giving you this chance. Okay? My other piece offering, which is probably a little bit smaller and less important to you, but I find this to be important. What I need to happen is for study habits to change. And so what I want you to do is reflect on your study habits. So I have added an additional homework that should take you like 5 minutes, probably max. It's 3 questions asking you to reflect on exam 1. It's due on the same exact date as homework 5, so that is a week from today. Due at homework 5 time, okay? So you have homework 5, and you have this bonus homework due next week on Thursday. Like I said, this bonus homework everyone should get 100, so it should boost your homework score. But I'm asking you to think critically about what you did do to prepare for exam 1, whether it worked for you, and what are you going to do differently, okay? Actionable items, not, I'm going to study harder. I want to know, how are you going to study harder? A better answer is, I'm going to make sure that I view every single recitation session and I work through the problems with the video. Okay? Remember, recitation sessions are posted on YouTube. This is a brilliant way for you to get more example problems. Working through all the different ways you can see this material tested. Right? So, I saw a lot of feedback about changing the recitation hours. Unfortunately, I can't change the recitation hours. Those are set. But that's why they're posted. Okay? So let's look at maybe the bell ringer feedback from last week. So I did look at all of the feedback, and I was able to categorize them into some common themes. The 2 main themes that I'm going to cover today is a lot of people ask for more example problems. Okay? And that's fair. However, I'm giving more example problems this year than I've ever given before because I'm doing recitation. Previously, I just had office hours, so people could come in and ask me questions. This recitation, I am finding problems for you that I think are important, and we're working through those solutions together, and I post the solutions and the notes on Canvas and on YouTube. That's your extra. However, if you want more, there are plenty more. So let me tell you a little bit about your book, if you have it. At the end of each chapter, there is this little orange section called Fundamental Problems. These are different than the red section labeled Problems. The reason that they're different is the small section of Fundamental Problems have the solution guide in the back of the book. Okay? Those 4-6 questions, those have solutions ready for you in the back of the book. You don't have to reach out to me for the solution guide, they're there for you. I will say the solution guides are not extraordinarily thorough. So if you're looking at the solution guide and you're still not like understanding how they got from one line to the next, email me. Email the TA. I am so happy to help you try to figure out how they got from one line to the next. That's absolutely doable. Reach out to me. It's fine. If you do these, and you are still gearing for more example problems, go to the red problem section. The red problem section does not have a solution guide, although these starred ones, there are a few in here that have little asterisks next to the number. Those have the final answer in the back. Just the final answer, not the solution. It doesn't work through any steps, but it gives you the final number you should expect. Okay? If you do the starred ones and you can't figure out how they got that final number, what should you do? No. What should you do?
Office hours.
Or email me. It doesn't even have to be office hours. Email me. I end up answering emails like ungodly hours of the day, okay? I will try to get back to you as soon as I possibly can to explain how they got that number. You can send me a screenshot of what you've already done and I can tell you where you went wrong. Okay? If you still need more examples, you've done all the starred ones, you still want to do more, pick any problem in the problem section and ask me for the solution guide. I have an instructor version of the solution guide with all of the instructions, okay? I will send that to you if you tell me what problem you want the solution for. Questions about any extra additional problems? Yes?
Will we ever receive our exams back?
You will, but I have a student who still hasn't taken the exam. They have to take it next week. So I have to wait until that student has taken the exam. Yep. If you want to come talk to me before then to see your exam because you don't want to wait, come to my office. I'll show you the exam. We'll go over it. Happy to go over it. Okay? I'm not going to do it in class because I have a precious few hours with you in class. Okay? I will post the solution eventually once that last student has taken the exam. And they're my solution guides, so it's like all the steps. Okay, next one. Give practice exam. I feel like that's a little bit different flavor than give more examples. The reason I haven't done that, and this is going to change from here on out as a teacher in dynamics for me, I have been reusing the same exams every semester. I don't want to create a new exam every semester. Do you know how hard it is to vet an exam to make sure everything is worded perfectly and is solvable and doable in exactly the right amount of time? It's hard. But I'm going to have to from here on out. Okay? There were some issues this semester. So, practice exam, I will do that, but I am not going to go through and make sure it's timed exactly right, that the problems are exactly the right difficulty as if it were the same exam. But I'll generally give you, this is a problem I think is probably good for this section of material, this problem is probably good, this problem is good. Okay? I'll do that. I'll post that before exam 2. Is that okay? Okay. There were a couple of other comments. There were some people I emailed directly to ask about some comments made. I think that's all I'm going to talk about for now. All right. Let's see. Last thing I want to do is announcements. You have homework 4 due today. I think most of you know that. Homework 5 is due a week from today. It's available. You should be able to do it. And then project module 1 is also coming up. I have posted corrections to that module, but at this point you should have the full complete module 1 instructions. I know that that document still needs work. It's a newer project than the exam that I created 3 years ago. So it's going through further revisions. If you find anything that is confusing, please email me, let me know. I'm happy to clarify anything that needs to be clarified. Any other questions before we dive into today's material? Okay, what I'm hoping to see is a lot more people coming to recitations. If not coming to recitations, then I'm hoping to see the view count on my recitation videos on YouTube skyrocketing. I'm hoping to see more of you email me to ask me for office hours. I'm hoping to be getting way more emails about homework problems before they're due, about helping you solve those homework problems in advance. I want questions. I want you to engage with me. I want to have a chance to help you past what is confusing, because I know this class is hard. Okay. All right, let's do some kinetics. All right, we're going to go back to my favorite equation of all time, the equation of motion. Equation of motion says the sum of forces equals mass times acceleration. If you would like it in words, this equation says that the sum of the external forces acting on the particle, we're starting with particles, then we're going to move to rigid bodies, is equal to the mass of the particle times the acceleration of the particle. Okay, so notice we're not talking about rotations. Why are we not talking about rotations or torques? It's a particle. It has no volume. It doesn't make sense for it to be rotating. Okay, it's a point mass floating around in space. Okay, so we are going to interpret this equation. We're going to interpret this equation according to each of the coordinate systems that we have covered so far. Okay, so we're going to have a Cartesian version of these equations. We're going to have a normal tangential version of these equations, and an r theta version of these equations. And it should be fairly straightforward. Okay, so if we were to break up this vector equation, notice my vector arrows. Vector arrows belong on the force and the acceleration, not on the mass. It's a scalar. If I were to break this up into components, one for each of the Cartesian coordinate directions, I would have that the sum of forces in the x direction is equal to mass times the acceleration in the x direction. Sum of forces in the y is mass times acceleration in the y. Sum of forces in the z equals mass times acceleration in the z. Okay, I just changed from a vector equation into a component-wise scalar versions of these equations. Okay, normal tangential coordinates are going to look very similar. The sum of the forces in the tangential direction equals mass times, what do you think? Acceleration in the tangential direction, A sub t. The sum of forces in the normal direction equals what? Beautiful. Samuel can follow a pattern. Hooray. M A sub n. This is where it gets interesting. This is where I say we do not lose any of our kinematics knowledge. Where here, acceleration in the tangential direction is equal to v dot. What is v dot in words? The time rate of change of, it's an S word. Speed, right? Velocity is a vector. The magnitude of the velocity vector is what we call speed. And v dot is the time rate of change of speed, the scalar. Okay? So just like we learned when we were doing only kinematics. And I have two examples for us today. The first one is going to involve the Cartesian coordinate system. Okay, I'm going to go ahead and tell you that the Cartesian coordinate system is a good choice for this one, and you'll see why. Okay? The way that we choose appropriate coordinate systems for problems here on out is we're going to look to see what quantities align with particular coordinate directions. So in this problem, what we're going to see is every single force that we're going to analyze about this system is either purely in the x direction or purely in the y direction. The acceleration, in fact, is also only purely in the, what direction do you think it is? It's going to jump up off the ground, or it's going to go back and forth? It's going to go in the x direction, right? So both of all of our forces and all of our accelerations are all purely in the x or the y direction. That's what makes this a good choice for the Cartesian coordinate system. However, in the second problem that we do, we're going to find sometimes we will come across problems where all of the forces align really well with one coordinate system, but our accelerations are more easily described in another coordinate system. What do you think we have to do to leverage both of those aspects? Change the coordinates. Beautiful. We've done it like 8 times before. We can do some trigonometry, right? We know trig. We can put one coordinate system on top of the other, figure out the angles between them, and do a coordinate transformation. And then our equation will be happy on both sides. Okay, well, let's jump into this one. Okay, we have a block A with a weight of 8 pounds and a block B with a weight of 6 pounds. They rest on a surface for which the coefficient of kinetic friction, mu k, is 0.2. If the spring has a stiffness of k equals 20 pounds per feet, it is compressed by 0.2 feet. Determine the acceleration of each block just after they are released. Okay? Very first thing I'm going to do is write down what's known. I'm going to write down that mu k is equal to 0.2. The stiffness of the spring is 20 pounds per foot. And delta S, or the compression, is 0.2 feet. Okay, so far in this class, we have not looked at 2 items that are connected by a spring. So this might be a little bit new for you. So here's the game plan. What we're going to do is we're going to draw 2 separate free body diagrams. One for the particle representing block A, and one for the particle representing block B. And we're going to analyze those free body diagrams separately. The thing that will be connecting them is the fact that we know how a spring provides force on a system. So the spring is going to push equally on A as it does on B. Okay, so we'll include that fact within our free body diagrams. Okay, so let's draw a free body diagram for A. Here's my block A. I have an 8. Now here's one thing that can be confusing in this class. Pounds are really weird in terms of whether they're a force or whether they're a mass. In this class, I want you to assume that you're being given a pound force, which means that the pounds force already incorporates the fact that gravity is 32.2 feet per second squared. So you can apply that poundage as a force in the direction of gravity. Okay? Now, kilograms is a mass. Kilograms you still have to multiply by 9.81 to turn it into a newton, which is a force. Okay? Okay, so block A has a weight of 8 pounds. That's one force that's on this thing. What's another force on this thing? Normal force, beautiful. Okay, I think the ground is going to exert a normal force like this, and I'm just guessing that it's up. All right, if we solve it and we get a negative number for n, it means I guessed wrong. What else do we have? Yes? Friction. Beautiful. So I'm just going to take a guess at what direction friction is going. I'm not told anything about the direction this thing is moving. However, I do know that the other force that's operating in the x direction is this spring that's in compression. When you have a spring that's in compression, does it push on or pull on everything it's connected to? Ooh, it pushes. I have a spring and I compress it like this. If I let go, do my hands go out that way? Yeah, so when a spring is compressed, the spring is pushing that way on everything that it's connected to.
I thought you meant like while it's being compressed, not like after it's released.
It doesn't matter. It's the same. When a spring is in compression, whether it's it's going to push. It's going to push on stuff. When you take a spring and you stretch it out, it's going to pull your hands towards each other. It's going to pull on everything it's connected to, okay? So this spring, I'm told it's compressed, so I'm going to give it a force like this. This is the F spring. And so since I have a force going that way, I'm guessing that this block is going to want to try to move to the left. So I would expect that friction is going to oppose that force. Okay? If you are not comfortable with free body diagrams, you have to fix it now. You will not succeed in the rest of this class if you are not comfortable with free body diagrams. Okay? It is the basis of everything we do from here on out. We are always going to start by drawing a free body diagram, and we will refer to that free body diagram when we write our equations. So if the free body diagram is missing a force, nothing else will be correct. Okay? Yes?
For the free body diagram, do you want us drawing them like this where it's a box, or could we draw it as a particle?
For this problem, we are treating these blocks as particles, so you can treat it as a particle.
Okay.
Right? Very good question. Okay, so in other words, I could have written it like this. Right? I could have put all the forces acting at a single point. Because for right now, we're not going to worry about torques or anything. Any other questions? Okay. So here's what we're going to do. I'm going to go ahead and start with this free body diagram. Once I draw my free body diagram, I'm going to start to think about summing my forces in each of the directions that make sense. So all of these forces point in either the X or the Y direction. So I'm going to say, oh, Cartesian coordinates seems like a good idea. So I will go ahead and sum, come on, pen, sum forces in the Y direction. Okay, so I'll say, actually, when we see blocks like this that are sitting on the ground, one assumption that it is safe to make, unless the problem tells us otherwise, it is safe to assume that the block does not leave the ground. Unless the problem tells me otherwise. This block doesn't leave the ground. So tell me about the acceleration in the Y direction. Right, the velocity in the Y direction is currently 0, and I just told you it's going to stay 0 for forever. So acceleration is always, well, sorry, not always. Acceleration for this problem, for this block, is 0 in the Y direction. So when I use that equation, sum of forces in the Y direction is MAY. AY is 0, so my sum of forces in the 0. In other words, it's static in the Y direction. So let's sum my forces. I see a normal, and I see 8. Oh, look, I can solve for my normal force immediately. My normal force is 8 pounds. Beautiful. Okay. I'm going to sum forces in the X direction. Okay. Sum of forces in the X direction equals MAX. Okay. I do suspect there's going to be some acceleration in the X direction, and I have no idea how much it's going to be. So I'm going to have to leave AX as a variable. I'm not going to be able to plug in a value for that. And in fact, I believe that is what is being asked of me. The problem is asking me to solve for the acceleration of each block. Okay, so let's look at forces in the X direction. I'm seeing a force of friction, and I'm seeing a spring force. That's all well and good, but I'm not actually going to write them down that way. I'm going to interpret a little bit about what it means to be a spring force, Does anyone remember from statics, what is the force from a linear spring? Yep. Yeah, K. I'm going to write it a little bit differently, only because we already have an X direction and a Y direction, and I don't want to mix up what this quantity is. This is not the X position. This quantity that you're multiplying by the spring stiffness is the amount that the spring is stretched or compressed. Okay, so this is the compression or the tension of the spring. Now, I'm going to be careful about the signs. What I do with springs is I don't let this tell me what direction the spring stiffness goes. Just like we did for like blocks on a pulley, I try to think more intuitively about how this spring is working, okay? So, we actually drew it correctly. We already thought through this process. We decided the problem tells me the spring is in compression, which means that it pushes on everything that it's attached to, which is why I drew this thing to the left on block A. So when it goes into my equation for the sum of forces, this spring force points in the positive or negative X direction. In the negative X direction. So I'm going to write it down as minus F spring. And in fact, I'm going to go ahead and plug in my spring stiffness, which is given to me, and my compression, which is given to me. So this is 20 times 0.2. This is my F spring. Okay. Force of friction, we had to take a guess. I suspect we made a good guess based on the forces that I'm seeing. So based on the way that it's drawn on our picture, does the force of friction point in the positive or negative X direction? It points in the positive X direction. So when I write it down, I say plus force of friction. But force of friction can also be written slightly differently. How can we write the force of friction? Mu K times the normal. Very good. Okay. So this is, whoops. Come on. Mu K times N. And this is great because we've already found N. If we hadn't already found N, we'd have had to leave it as a variable. But we found it in that first set of equations. So this is 0.2 times 8 equals mass. In fact, what is the mass of the block?
8 pounds.
Ah, now I told you that 8 pounds is a force. Yes, so to find the mass of the block, I need to divide by 32.2 feet per second squared. So I'm going to leave it that way in my mass equation. So just to be a little clear, this is pounds force, and this is feet per second squared. So that's G. And this is acceleration in the X. Yes, question?
So even though it says weight in the problem statement, we assume that what we're given is the pound force, and then we have to go and convert it into mass when we get to this point?
Yep. Yep. Yep.
So will the book ever give us a pound force? Is it just a pound that we're supposed to assume is a pound force?
Yeah, so unfortunately the book always just writes pounds. But I'm telling you now, anytime they give you pounds, it means pounds force. Anytime you see pounds, it means pounds force. They will never give you pounds mass. Okay, so I see one equation and one unknown. That makes me very, very happy. That tells me that I can solve for AX, which is specifically for block A, is equal to minus 9.66 feet per second squared. What does the minus sign tell us? It's telling us that it's accelerating the opposite direction of our positive X, right? Which we defined. We chose this to be true. We could have chosen this. And in fact, if we had chosen this and I had done the exact same set of steps, I would have solved for AX would be a positive 9.66. Okay, so you must show me where you are pointing your coordinate system. It's the only way for me to check that your signs are right. Okay, so we assumed the direction that I think is usually most common for X and Y. Okay, so we found the acceleration for the first block. I believe the problem still wants the other block. So now, what do you think is our first step to do that? Draw a free body diagram. I tried to combine too much material today. I think I'm going to run out of time for the second example because I've been trying to belabor fundamentals in this problem. So I'm probably going to redistribute. We will come back next class and address the problem that I wanted to do today, but I feel like we're making good progress on understanding this very completely. So we're going to keep going nice and slow on this problem, okay? All right. So we're going to draw a free body diagram for block A. Sorry, block B. I'm sorry. Block B. Okay, now would be a good time to test yourself to see if that you can do it yourself. Okay, test yourself, see if you can draw the free body diagram of block B. Okay, ask yourself, did you get it or did you forget some forces? This method of testing yourself, this is a really strong study strategy. So think about what's being asked of you in an exam. You're being asked to solve a problem from start to finish that you've never seen before without any help from professor, from the book, from your notes, nothing, okay? So you need to be testing yourself before the exam to see if you are able to do that correctly. So you should test yourself, how far can I get in the problem before I am so stuck that I need to go find a different resource? If you made it 10% of the way through the problem before you got so stuck you had to go find help, you're not ready for the exam. If you made it 50% of the way through the problem before you had to find another resource, you're not ready for the exam. Until you can solve a question from start to finish without using any additional resource aside from your equation sheets, that's when you're ready for the exam. So testing yourself, always trying to figure out where am I at in my understanding. From the moment that you're in class, testing yourself in class. When you're doing homework, testing how far you can get in homework. When you're doing extra practice problems, how far are you getting in practice problems? Okay, that's how you gauge for yourself whether you're ready. All right, next step. What's my next step? It's the exact same as for block A. Sum of forces in one of the directions. I'm going to pick Y because that worked out well for me last time. Sum in the Y. Yes, question.
On an exam, are you going to look for us to sum it in the Y, or can we just say let the normal forces? Like, are you going to look for, do I have to write out the full? The more work you show me, the more partial credit I can give you. If you answer, so here's what I often do. What I will often do is, and you'll see this in my solution guide, I will write out my solution guide and I will give points to each line of work. One of those that I often assign points to is, did you write sum of forces in the Y direction out correctly? Right? Did each of your forces point in the right direction? If it was safe to know which direction it points ahead of time. I get points for that. So if you end up with the wrong value for n, and you didn't write down your sum of forces in the y, you're not getting any points for the value of n, and you're not getting any points for that equation. Okay? The more you write out, the more points I can give you. Okay, sum of forces in the y equals n minus 6 equals 0, n equals 6 pounds. Beautiful. I'm going to need that 15 feet per second squared. Okay, this was a super straightforward problem. Why was it super straightforward? Well, every time I wrote a sum of forces equation, I was immediately able to solve for the value of a variable. That's straightforward. Guess what's not always going to happen? That. You're not always going to be immediately able to solve for a variable. So how many equations did we write? If I'm counting correctly, we wrote 4 different equations. We wrote an equation for the sum of forces in the x for block A. We wrote an equation for sum of forces in the y for block A. We wrote an equation for the sum of forces in x for block B. Sum of forces in the y for block B. That's 4 equations. Guess how many unknowns that means I can solve for? 4. We can solve systems of equations where sometimes there are 2 variables in the same equation that I don't know the answer to, but as long as my unknowns equals the number of equations, I can solve that system. I know for a fact I'll be able to solve it, and you'll solve it and get the right answer. Okay? So that means that sometimes when you write out the sum of forces in the x, one of these things is going to have to stay a variable. And then you will need to say, pause, this is okay. I am okay with this. I need to continue writing the other equations that I know to be true. Okay? Then, once I write all the equations that I can possibly think of doing, I compare variables to equations and see if I'm happy. If I'm not happy, if I don't have equations equals to unknowns, more often than not, I have missed some piece of information in the problem statement. This happened in the exam a lot. Okay? There are key pieces of information. If you are reading the problem statement and it says something and you're like, why the heck would it say that? So for an example, in the projectile motion problem, is Jamie in here? Okay. If the projectile motion says that at the moment I'm asking you about, you are at the peak point of your trajectory. If you don't write down an equation that goes with that piece of information, probably means you're missing something. Okay? So if you read that and you're like, oh, that's great, why I don't care, why would I care that it's the peak of the trajectory, you're not going to have enough information to solve for all the unknowns. So what does it mean? What equation could we possibly say is true that captures the fact that at that instant, the projectile is at the top of its height? Samuel?
The velocity of the y is 0.
It means that at that instant, the velocity in the y direction is 0. If you didn't catch that, you were not able to solve that problem. Okay? So, this is another strategy for exams. You will use every piece of information that they give you, for the most part. Okay? Okay, that's the best strategy I think I can give you. So, let's look at our next problem. It's going to look a little bit familiar, but we're not going to be able to finish it today. Actually, sorry. I want to give you one extra piece of information that will be useful for our next problem. Okay? So, we have talked about, for the most part, when we have done coordinate transformations in this class, we have taken a radial and transverse coordinate system, and we have, usually within the picture, we're given the angle that something makes with like the vertical or the horizontal, right? We're given some angle that relates that coordinate system that we want to use with like a Cartesian coordinate system that we're going to have to use for some reason. Sometimes that's not going to be given to you, but you still need to form a relationship or find the angle between two different coordinate systems. So here's a small piece of information that we will have to leverage for those types of problems. Okay, so we're going to say a useful value if you ever need to convert. Oh, got unplugged here. If you ever need to convert between, specifically between an r theta coordinate system and an n t coordinate system, we're going to learn about a very special angle called psi. This angle psi has a relationship between both the radial and transverse and the normal and tangential direction. And the equation that you'll need to use is that the tangent of psi is equal to r divided by dr d theta. And we're going to need a picture to go with this. So I am drawing an origin, and this particle, I usually do particles blue, so let's change this to the particle. I'm going to draw the path that this thing is moving on, so maybe it's on some curved path like this, and maybe it's moving up and to the left. I'm going to draw the two different coordinate systems that I could possibly draw for this. I could choose to look at this in terms of normal and tangential coordinates. And the tangential direction goes tangent to the path in the direction of motion, and then 90 degrees from that into the curve, my normal direction. The other system I could choose is I could look at the radial direction, which goes from the origin to the particle and then out past the particle. Okay, if I define theta like this, my u hat theta points something like this. This is clockwise, this is counterclockwise, from u hat r to u hat t. Counterclockwise from u hat r to u hat t. This here is psi. Okay. What makes talking about psi a little bit weird is if you were to solve this equation for tangent psi equals r dr d theta. If you get a negative value for psi, what you're actually being told is the opposite direction. So if you get a negative value for psi, you're actually being told the angle that goes clockwise from u hat r to the negative u hat t. So this is the angle you found if psi turns out to be negative. okay? So you're going to have to use this equation and be able to essentially draw where that psi is on this graph. And the whole reason is because for some problems, our forces are going to be beautifully in the normal and tangential direction, but we're given things that allow us to write accelerations very easily in the r theta direction. We have to be able to convert between the two to get everything into a common coordinate system, okay? The only way we can do that is if we know some angle between these two coordinate systems. This is how you find the angle between the two coordinate systems. You solve for psi, okay? All right, so here is the big problem that we're going to work on. It's familiar because I had you work on the free body diagram during our bell ringer. And in fact, let's go back to our bell ringer. I'm going to turn back real quick. And in fact, someone asked this beautifully. They asked about the relationship between the normal force and the normal direction, the normal coordinate direction. Okay? So also let's look at what they told us about P. So early on in this class, we said, okay, the normal force does point along the unit normal direction, but it actually points in the opposite direction, right? So it's in the negative u hat n direction. The P force, we're even told that the P force is tangential. So P here aligns perfectly with the tangential direction, u hat t direction. N aligns with u hat n, P aligns with u hat t. I'm starting to think normal and tangential coordinates might be nice. Yeah? It's a great first thought. However, when I get back to the problem statement, I'm not given the things about acceleration that make sense for a normal tangential coordinate system. If I wanted to use the normal and tangential coordinate system here, I would be looking to fill out those accelerations. So let's go grab our normal tangential accelerations. I need to find things like v dot and v squared over rho if I'm going to use this coordinate system for this problem. Let's go look at that problem statement and see if we can find v dot or v and rho. I see an angular rate. That's not either of the things I'm looking for. I'm looking at the instant where a theta equals a 90 degrees, and I'm given some r. Those are not the right variables. Guess what variables they are right for? My r theta system. Okay. If I instead say, okay, well, my forces are in the nt directions, but my accelerations, can I find that? Well, let's see. Can I find an r? Yes, it's given to me in the problem. Can I find a theta dot? Yes, it's given to me in the problem. Can I find a theta double dot? Well, it tells me the angular rate is constant. Okay, so that means that angular acceleration is 0. Beautiful, there's theta double dot. Can I find r dot? Can I find r double dot? Well, we're going to have to do some chain rule, but the answer is yes. Okay? So here's what you're going to be tempted to do. You're going to be tempted to say, my sum of forces equals mass times acceleration. And you might say something like, this is P in the u hat t direction plus something like N in the u hat n direction. This is equal to mass times r double dot minus r theta dot squared in the u hat r direction plus r theta double dot plus 2r dot theta dot in the u hat theta direction. And that gets me nowhere, because I cannot combine u hat t's with u hat r's or u hat n's with u hat thetas. Okay? It's okay to start here, but then I need to do my coordinate transformation steps like we've done before. So what I need to do is decide whether I'm going to put everything in terms of the u hat t and n system, or I'm going to put everything in terms of the u hat r and u hat theta system. Then what is my step for doing coordinate transformations? I always do the same steps every time. Who's seen me in office hours and I've walked through coordinate transformations? I draw something. Yeah?
You take one of them and set those basically like equal to I and j, and then you'll go.
Okay, you're describing specifically converting to a Cartesian coordinate system, okay? But what I just gave you here for psi is going to allow us to cut out the middleman. We don't necessarily need to convert t's and n's into i's and j's, as well as r's and thetas into i's and j's. We can actually make it a little bit simpler. Because I have psi, I can go ahead and just convert one into the other. Right? I can either turn r's and thetas into n's and t's, or I convert n's and t's into r's and thetas. Because I have psi. But still, the same steps always follow. When I do a unit direction transformation, I always draw both coordinate systems right on top of each other, really big, somewhere else. I'm going to say that over and over and over again every time we do a coordinate transformation. How do I do it? Coordinate transformation. 1. Draw both coordinate systems. Really big. Why do I say really big? Because I see a lot of times, especially on exams, people draw all these itty-bitty little tiny coordinate systems, and then it's really hard to tell what you're drawing angles for, and angles get misassigned, and the trig comes out wrong. But if you draw it nice and big, there's no restriction on paper in this class. You can use as much as you want. You can draw it really big. Everything becomes a lot clearer, a lot less cluttered, and a lot less likely to make mistakes. Okay? So I draw both coordinate systems really big, right on top of each other. Somewhere else. When I say somewhere else, I mean don't draw it on the picture of the system itself. Don't draw it there because it gets really cluttered, it's really small, and I want you to have lots of space so that you can see exactly where these angles are and everything else. So I'm going to do these steps with you right now. Okay? So I have this path that's describing the rod. I have this collar. I have an origin that's defined for me slightly off to the left. And theta is measured relative to the horizontal, like this. So I'm going to make this even bigger. Let's draw both coordinate systems again. U hat R. U hat theta. U hat tangent. U hat normal. And in fact, I'm going to draw the negative directions for each of these vectors as well. Okay, if I'm going to do a coordinate transformation, I need to know what one of these angles is. And I'm not told that in the problem. However, I am given enough in the problem statement to solve for psi. Okay, so by definition, psi goes from u hat r to u hat tangent. This is psi. And tangent psi equals r over dr d theta. Do I know what r is? Yeah. I'm given that r is equal to 4 over 1 minus cosine theta. And I'm asked specifically at the moment where theta equals 90 degrees. Can I find dr d theta? Yep. I have an expression for r in terms of theta. I can take the derivative. Okay, this should be 4, 1 minus cos theta. Whoops, sorry, I put my negative on the wrong spot. This is minus 1. So this is 4 minus 2 times the derivative of cosine should be negative sine, but we already have a negative here. So I'm guessing we multiply by sine of theta. Did I do that right? Yep.
Was theta given to us in the problem?
Yes, yes. It says, it's asking if the angular rate is constant equals theta equals 4 radians per second squared. Determine the tangential force to cause the motion and the normal force component that the collar exerts on the rod at the instant where theta equals 90 degrees. Okay. All right. What is cosine of 90? 0. Okay. So that means r equals 4. I have a 4 over 1 minus 0. Is that right? What is dr d theta? Negative 1. Or should it be negative 4? Negative 4. Okay, so I get that tangent psi equals 4 over negative 4, which is equal to negative 1. Tan inverse of negative 1 will equal psi. So we should find that psi is equal to minus 45 degrees. Okay, so we solved and we found a negative value for psi. So it means that psi does not in fact go from u hat r to u hat tangent positively. It goes clockwise from u hat r to the negative u hat tangent. So this is psi and it's equal to 45 degrees. Okay, at this point, we have to decide whether we want to convert everything into r thetas or we want to convert everything into NTs. What are we thinking? Okay, 6 to 1/2 dozen the other. I'm going to say we're going to convert everything into normals and tangents. Okay, so that means that I need to use this picture to write u hat theta in terms of some amount in the tangent direction and some amount in the normal direction. Okay, so we'll see that we have some amount that goes in the positive tangent and some amount that goes in the negative normal. And then I need to do the same thing for u hat r. So I need to find how much of u hat r goes in the negative u hat tangent direction and how much of u hat r goes in the negative u hat normal direction. Okay, so in other words, I'm going to seek out an expression for u hat theta that involves u hat t and u hat n. Similarly, I'll find an expression for u hat r that does the same. Okay, so the magical thing about putting these coordinate systems smack on top of each other at the same place is that every other wedge is the same angle. Okay, so if this wedge here is 45 degrees, it means this is 45 degrees, this is 45 degrees, this is 45 degrees, okay? Now, they're actually all 45, right? Because 45 plus 45 is 90. That forms the rest of these right angles. So when I look at these triangles that I'm trying to use for my trig, I now know that this is 45 and this is 45 degrees, okay? So now I have everything that I need to write these expressions, to convert everything into the normals and tangents, okay? All right, why am I doing this super complicated problem? We've talked before about why do I do this where I try to make problems that use both coordinate systems. Because it allows me and you to test whether you actually understand both coordinate systems within one problem, okay? That's why I like these problems. I can test a lot of things with the same problem. All right, thank you for being here. Please reach out by email if you need to talk to me.